You've chosen to do the additional topics over triangles. This section will be covered more in depth when you get to geometry class. A big part about this additional topic is a lot of vocabulary words. I'm not going to cover all of them, but a lot of them are on here that you'll see next year. So first, let's take your highlighter, highlight scaling triangle. It's a triangle having 3 sides of different lengths. For example, 5 centimeters, 4 centimeters, and 2 centimeters. Okay, the second one, isosceles triangle. An isosceles triangle is a triangle that has at least 2 sides of equal length. It could be all 3, but isosceles is definitely 2. Also, you will know that these 2 angles will be the same because of that. Okay, the next one is equilateral, regular triangles. It's a triangle with all 3 sides of equal length. Also, in addition to them being equal length, you'll know that each angle is congruent. They're all equal to 60 degrees. An acute triangle is a triangle whose all sides are acute. They're all less than 90 degrees. Here's an example of that. A right triangle is a triangle whose angle has a right angle. Basically, it has a 90-degree angle. Obtuse triangles is a triangle that has an angle that's obtuse, is greater than 90 degrees, such as 120. The angle of a straight line is 180 degrees. The degrees of a circle is 360 degrees. The interior angles of a regular polygon is theta equals 180 times n minus 2 all over n, where n is the number of sides. A polygon is a plane-closed geometric figure with 3 or more sides. On the next page, you have some triangles here, A, B, and C. You can also say cosine, sine, and 1. Your reference angle is called theta. So we're going to name each of these sides. A and B are also known as legs, and C is the hypotenuse. So opposite, abbreviated OPP, is the side opposite of the reference angle. It's the side B. It's the side that's opposite of theta. It's also called Y commonly. Adjacent, abbreviated ADJ, is the side next to the reference angle. That's usually called side A, also known as X. You also say cosine theta. And then the hypotenuse, abbreviated HYP, is the longest side, and it's the opposite of the 90-degree angle. It's also known as R, and a lot of times it's 1 if you're referring to a unit circle. Now, to determine if a triangle is right-angled, obtuse angled, or acute angled, without knowing any of the angles, but knowing all 3 of the side lengths, you can put it into this formula: a squared plus b squared and c squared. Depending on the relation symbol that holds true for this statement, that determines if it's right, obtuse, or acute. For the triangle inequality theorem, it's used to determine if 3 given side lengths can form a triangle. And for this to happen, all three of these conditions must be true. A plus B must be greater than side length C, A plus C must be greater than B, and B plus C must be greater than A. Basically, each combination of two side lengths added together must be greater than the other side length. We have Pythagorean theorem, a squared plus b squared equals c squared. That's in the case that's a right triangle. We also have something called Pythagorean triples. They're right triangles that have integer lengths a, b, and c. So no decimals, no irrational numbers, none of that. Some common examples are 3, 4, 5, 5, 12, 13, 7, 24, 25, and 8, 15, 17. Some special right triangles are 45, 45, 90, and our 30, 60, 90 triangles. They will follow these formulas that are on here for the side lengths. The area of a triangle is area equals 1/2 base times height. You can also use Heron's formula to find it a different way if you don't know some of this. We have area of an equilateral triangle, and then the perimeter is the distance around. Complementary angles are angles that add up to 90 degrees, such as this picture, and supplementary angles are angles that add up to 180 degrees, such as this one. Triangle angles are supplementary. All three sides together add up to 180 degrees. Here's some more vocabulary. So we have a median. It's a segment whose endpoints are a vertex of the triangle and the midpoint of the opposite side. And then the intersection of the medians is called the centroid. The altitude is the perpendicular segment from a vertex to the opposite side. It forms right angles. Orthocenter is the intersection of these altitudes. To bisect means to divide into two equal parts. The dividing line is called the bisector. Perpendicular bisector is a segment, line, or ray that is perpendicular to a side and passes through the midpoint. The circumcenter is the intersection of perpendicular bisectors. Right here. On the next page we have congruent triangles. Here's an example of what that would look like. All the sides of one triangle are equal to the corresponding sides of another triangle, and the corresponding angles are also equal. All congruent triangles are also similar triangles, but the converse is not true. It basically means that not all similar triangles are congruent. Similar triangles, the corresponding angles of two triangles are congruent, and the lengths of the corresponding sides are proportional. They're scalar. So for similar triangles, they have equal angles, but they do not necessarily have equal side lengths, although the side lengths are proportional to each other. Like if you multiply this side length by 2 to get this side length, you also have to multiply this side length by 2 to get this side length. Now here's some properties to prove these. To prove similarity, you can use angle, angle, also known as angle, angle, angle. So here's an example for that. Notice all three of the angles are the same, and you would multiply this triangle by 2 for each of the side lengths to get the new side lengths. Vertical angles are congruent to each other. So that means that angle D is equal to angle C, and angle A is equal to angle B. All four of them together would give you 360 degrees. Reflexive property is the side or angle measurement is congruent to itself. In this case, this side length AB is equal to itself. You can use that if you're trying to prove that both these triangles were congruent or similar. Of course, you would need more information than that, but that's somewhere you could start. Now the side theorem, we have if three sides of a triangle are equal to the corresponding three sides of another triangle, the triangles are said to be congruent. And if the sides are proportional, the triangles are similar. So you can use this theorem for both congruence and similarity. Now with angle, you can only prove it for similarity, not congruence. We have side, angle, side, SAS. If two sides and the angle included between the two sides of a triangle are equal to the corresponding two sides and the included angle of another triangle, then the triangles are congruent. And then you can use this theorem to prove that they're similar if those side lengths are proportional. Basically, if they have a common ratio between both of them. And then we have angle, side, angle. If two angles and the included side of a triangle are equal to the corresponding two angles and the included side of another triangle, then the triangles are congruent. Now from this, since we know two of the angles already, we can already conclude that the third angle must be congruent to each other because the angles have to add up to 180. So to prove that it's similar, you could just go back to this theorem. So let's try one of the exercise practice problems on the back. So we have these two triangles. They're not necessarily drawn to scale. And we have three and 4 and an angle, and we have 3, 4 and an angle. These angles are 90 degrees. So, are these triangles scalene, isosceles, or equilateral? Well, we have a 90-degree angle, so we know that this side must be bigger than 3 or 4. So that means that all three side lengths must be different. So that's scalene. Acute, right, or obtuse? Well, we have a 90-degree angle, so that's automatically right. Congruent, similar, or neither? Well, these are congruent, even though it doesn't look like it. In geometry, in the textbook, there will be a lot of triangles and quadrilaterals that look the same or look different, and they're not necessarily that. Now, the theorem that we use to prove that they're congruent would be side, angle, side. This theorem. So put S, A, S. So try the rest of these on your own. If you can't determine one of these, you would just put cannot be determined.